Welcome to Google Cloud AI Developer Relations Virtual Training. This is part 3 of our primer. My name is Andrew Furlich, and I'm a member of Google Cloud AI Developer Relations. So let's go ahead and get started. So we're in part 3 now. In part 1 and part 2, we talked about building models, and we did a little, or referred to a little bit about training them, but in this part, we're going to establish the foundation for how to train a model. So the models we've been working with so far are known as forward feed models. That is, we take our training data and we feed it from the input layer forward to the output layer. And then at the output layer, we calculate what we call a loss. That is, the model makes a prediction of what it thinks something is, or how, and then we have the real answers, we call that the ground truth, and we compare the difference, or the loss between them. And then we're going to want to take that loss and we want to backward propagate through the model and update the weights such that the next time we put a batch or training data through, that loss is smaller. And we want to keep repeating this, making the loss smaller, 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 and smaller. So let's describe this in a little bit different terms. So what we want to do is we want the model to perform well when it's deployed. Okay, and we're going to deploy it in the real world, and that means it's going to see examples it was never trained on. Okay, your data set, in a sense, is a subset of the real world. And we're going to call the real world the population distribution. And population distribution just means if you had every example there was in the population. And a sampling distribution means you just have a subset of it. So let me give you an example. Let's say you were working with a data set that related to the shoe size of every male in North America. If you actually had the shoe size of every male in North America, that would be a population distribution. But if you had only a subset, a few here, a few there, a few here, and a few there, that's a sampling distribution, and that's what your data set is. Now, that data set, or that training data, is going to consist of two parts. The features, which are also known as the independent variables, and in the case of computer vision, those are your images. And the corresponding labels, also known as the dependent variable, and sometimes referred to as the ground truth, the correct answer. So our goal, of course, is to train the model that once it deploys, given examples without the labels, the ground truths, from the population that it has never seen before, the model is generalized that it can accurately predict the label, i.e. the correct answer. And this latter step is known as inference. Okay, so let's talk a little bit about feeding. So we've talked about we have this training data here, and we're going to feed it through the model. And what we do is we break it up into batches, and we're going to feed a batch at a time through the model. And every time a batch goes through, we're going to calculate the loss. Now, these batches are actually formed in random, but no example in here appears in more than one batch. Or in other words, every example in here appears only in one batch, but what's in a batch is randomly drawn from the training data. And then what we're going to do is once we fed all the training data through it, that's called an epoch, and we're going to keep repeating this a number of times. That is, a number of times we're going to feed all the training data as batches. But each time we do that, we'll get a different set of batches. So even the batches, how they're drawn from the training data, are randomized each and every epoch. So no two epochs see the exact same ordering of examples. So on the backward propagation part, we take our batches, We feed it through. After every batch, we're going to calculate a loss. We have a loss function that calculates a loss. Then we're going to take that value to our optimizer. And it's in our optimizer that's going to update the parameters, also referred to as the weights of this model. And the job of the optimizer is to find an optimal way to update the weights to get closer to the correct answers on subsequent batches. So let's move into now data sets. I'm going to start you off with the concept of a curated data set. Think of it as something that's essentially perfect. Okay, so it's a data set. It's a collection of examples that are very large and diverse enough to be representative of the population, okay, that we're going to model. And the data set meets this definition and is clean, has no noise in it, and is ready, format ready for machine learning. We refer to those as curated data sets. And those are usually the data sets that we use for academic and educational purposes. You've heard of them a lot of times, things like MINTS, CFAR10, cats and dogs, etc., etc. And we'll start you off with those, and then we'll move into real world data sets. So the first thing we need to do when we got a data set is we need to split it. Some of it's going to be used for training and some of it's going to be used for testing. And we're going to make assumption that our training data is a good sampling distribution. That is, it's representative of the population distribution. Therefore, the accuracy on the training data should reflect the accuracy when deployed to the real world. But how do we really know this is true before we deploy the model? And that's the purpose of the test data. We're going to hold it out, also referred to as a holdout data, and we're never going to train the model on the test data. When we're done training the model, we're going to use the test data to predict how the model would do once it's deployed. Now, there are various sort of rules or methodologies of how to split the training and test data, but for this purpose, I'm gonna start with a historical rule. It's kind of arbitrary. It was you took 80% of your data for training and 20% for test. So, assuming this is our curated data set here, we first want to randomly shuffle. And here's an easy reason to think of. Let's say our data set consisted of fruits, apple, pears, bananas, so forth. There were 5 different fruits ending with oranges. And if the data was in sequential order, and let's say we had the same number of examples for each, 1,000 of each, and we took the first 80%, we're going to take 4 fruits, all the examples, and the test data would be the last fruit, which would be a different one, say an orange. So your model would only be learning on the first 4 fruits, but be evaluated on a fruit it never learned on. That's not going to work. So what we need is both the training and the test data to have the same distributions. And the simplest way to do that is just to randomly shuffle them before we split. So I'm going to use a simple example here to get you started. As I always mention, I rarely or infrequently refer to MINTS because it's so basic, but it's good for a first step. So what we'll do here is we're going to import the built-in MINTS data set to Tensorflow+Keras. So from Tensorflow+Keras data sets, we're going to import MINTS. This data set is a curated one. That means it's already automatically randomly shuffled and pre-split into train and test data. So we're going to invoke the load data method to get that. And now it's going to give us 2 tuples. The first one is the training data. The second one is the test data. It follows a common convention. We generally use X to mean the features, Y to mean the corresponding labels. So these are the images, and these are the labels that go with the images. So we'll put together a real simple model for MINTS and compile it. So we create our sequential object here. Recall that generally one of the more optimal ways of doing MINTS is 2 dense layers of 512. And of course, you have your output layer has 10 nodes for the 10 digits, 0 through 9. And because it's a multi-class classifier, our activation function is going to be a softmax. Okay, but this is a DNN, and as you recall, a DNN can only take a 1D vector as input, and our images are a 2D matrix, 28 by 28. So we're going to add as a first step the flatten step to flatten those images into a 1D vector. So let's go ahead and train it. Now, if you just did it like this, you might be, back up. So this is the fit method, and that's what we use to train. It may seem odd to you why they call it fit when like train be a better name. It's kind of a historical name, and it comes from the premise of you're going to fit the model to the data. Okay, and what we want to do is give it the training data and the corresponding labels. Well, in this example, if I did that, I would actually get an error message. And let's kind of look at what happened here. So it's referring to my labels here, because that's it's referring to the loss on the categorical cross entropy. So it's clearly the labels it's talking about. And it's looking at, it says, is it got a shape of 60,000, comma 1. What does that mean? Well, that means that we had 60,000 examples. And for those 60,000 examples, we represent them by a scalar value. That is the digit 0 through 9. So why did this fail? Well, it failed because our model doesn't have a single output node. It has 10 output nodes. If it was a single output node, it'd be like a regressor or a binary classifier. And when you have multiple output nodes, your label has to align with all of them. So in the case of the 10 output nodes, our labels need to be a 1D vector, 10 elements long. And every element is going to correspond to the corresponding output node. So the first element is the first output node. The second element is the second output node, and so forth. And what we want to do is we're going to do this thing called one-hot encoding, where we're going to convert these scalar values to these one-hot encoded labels. And that means I'm going to, in our case, going to create a 1D vector. And I'm going to put a 1 in the location that refers to the correct answer, and a 0 everywhere else. So in this case, this is the label 0, so I put a 1 there. This is a label 3, so I put a 1 there. This is 7, 8, 9. This is a label 6, so I put a 1 there. And that refers to as one-hot encoding. Now, the nice thing is you don't have to do this yourself. It's actually a method built into Keras for doing this. So from Tensorflow+Keras utils, we're going to import the two-categorical method. And all we need to do is to pass our training and our test data, both of them to two-categorical, and say the number of classes. That's how big the 1D vector is going to be. And because it's mint 0 through 9 digits, it's 10 classes. Now, when we invoke the fit, we don't get an error message, and it looks a lot better. So right at the beginning, we will see something that looks like this. So we have trained it for our 60,000 went through for an epoch, and we got approximately 90% accuracy. Pretty good to start for the first epoch. Now, we could have done this differently. In Keras, it's actually built into the fit method to dynamically do the one-hot encoding. So I could have skipped this two-categorical step by changing my loss function. So instead of saying categorical cross entropy, I'm going to say sparse categorical cross entropy. That means I can just give it the scalar values, and it will dynamically do the one-hot encoding for me. So let's go back to the same example where I pull the data out without one-hot encoding the labels, call my model.fit, and because I compile it this way, I don't get an error message. And now when I get down to, let's say, the 10th epoch here, we have about 97% accuracy. Not bad at all. But that also brings us to the problem with large numbers. And that's not so bad on MINTs, but it is on other data sets. And what I mean by it is when we pull that data out, that we loaded that data, all the values, the pixel values, were in their still original range of 0 to 255. And as I've mentioned many times, within the model, the weights and biases typically tend to be very small numbers, somewhere between -1 and 1. Well, those large values times those tiny little numbers can really cause wild swings in the model and make the model unstable and difficult to train, especially as you're going through multiple layers. And at best, this will result in taking longer for the parameter to learn the optimal values, and in some cases, they may not even learn at all. So how do we address this? Well, we're going to do normalization. And that really means is we're going to take our input values and we're going to squash them into a range so that the range is comparable to the same range of the weights, so we don't get these wild swings. Okay, so the most basic way of squashing is to proportionally change the weights into a range between 0 and 1. And since our values are between 0 and 255, all we need to do is divide our training data, our elements, by 255. And there we're going to replace every one of those integer values with a value between 0 and 1 that's proportional in this range. Now, these are NumPy multi-dimensional arrays. Those are implemented as a class. They do polymorphism on mathematical operations here. And so this division here will automatically get broadcasted to every single element in the array. NumPy also does all its floating point operations as double precision or float 64, but we really want it only as float 32. We don't really want to double the number of instructions we need at that input layer. So we're going to recast it after the operation back to a float 32. Now let's repeat that same model fit on our training data. Okay, 10 epochs as before. And now when we run it, we can see instead of getting 97% accuracy, we got 99.4 when we normalize the input data. We do even better. Okay. So people have different forms of squashing that they prefer. Some people prefer, instead of squashing between 0 and 1, is to squash between -1 and 1 and center your data on 0. Well, to do that, we just change this a little bit. Instead of dividing it by the max value, we divide it by half the max value. In this case, that'd be 127.5, and then subtract 1. Another form of normalization is called standardization, and this is considered to give a better result, but it requires a pre-analysis or a scan over the entire input data. Okay. So what you do is you're going to find the mean and the standard deviation of the entire input data. You're going to center the data at the mean of the full distribution of the input data, and then squash the values between plus or minus 1 standard deviation. And we can do that all with NumPy. So we're going to use the mean method in NumPy and give it the training data. It's going to go through all that pixel data and calculate the mean value across the entire training data set. And then we're going to use the standard deviation method to find the corresponding standard deviation. So now we just modify this statement here as we did before, but now we're going to subtract the mean, and then we're going to divide it by the standard deviation. Okay, so far we've talked about splitting the training data or our data set into training data and test data, also known as the holdout data. And at the end of the training, we're going to look at run the test data to see if we're getting the same accuracy as we did during training. Okay, and this assumes we're not. Let's say the model overfitted. It looked great on the training data, but when we run on the test data, there's a big gap in accuracy. Did you really want to get to the very end of your training before you know that? Wouldn't it be nicer that as you're training, you had some indication that you were about to or were overfitting? And if you saw that, you could at least terminate the training early. Well, that's what validation data is about. So what we do is we take our training data, and then we're going to take a tiny amount out. Excuse me. We take a tiny amount out and set it aside. Oh, I'm having a problem here. My screens. Okay. So we're going to use the training data without the validation data for training. And then at the end of every epoch, we're going to run the validation data through that was never used for training to sort of guesstimate what the accuracy would be or the result at the end when we did with the test data. So again, what we're looking for is the loss and the accuracy in the validation data to be comparable to that of the training data. And if we suddenly see a big gap or degradation, we know something is going wrong at that point in the training, and we can just terminate it. So how do we do that? Okay, so in this example from Tensorflow+Keras datasets, we're going to use the CFAR10. I'm going to load that. I'm going to do my normalization here. And now when I go fit, I'm going to add in a new argument. This is a keyword argument called validation split. I'm going to set it to 0.1, which means take 10% of the training data and set it aside and use it as validation data. So let's go ahead and look what happens when you're overfitting. So I took that example, and we're going to run it 15 epochs. And I haven't done anything special to prevent overfitting. So around the fourth epoch, you can see our loss is 1, and our accuracy is 63%. Now, because we did validation split, we're going to see a little bit more to output. We're going to see the corresponding loss and accuracy on the validation data, and you can see they're effectively the same. No idea why it's doing that. On our fifth one, we see it start to deviate. We see the accuracy was 65, but it actually went down a little bit on the validation. Kind of suspicious. By the time we get to the 15th epoch, we see a big gap. We have almost 75% accuracy, but we never really changed the accuracy on the validation data. It's still around 63. What really means that somewhere around the 5th epoch, we started to diverge, and we're likely started memorizing the training data and overfitting to it. Okay, so with models, we want to go deeper with layers to get better accuracy. And one of the problems with that is we could introduce instability in the model, even if we address these with techniques such as identity links and batch normalization. And this is really because many of the values we are going to do a matrix multiply with are less than the number, are very tiny numbers. And multiplying two tiny numbers less than one gets you an even smaller number. So one of the very first problems you could have going deeper with layers is that the hardware can't represent that number anymore. And we refer to that as the vanishing gradient. But we can have other problems too. If every weight in your model had the exact same value, that is perfect symmetry, that's really the same thing of having only one node, and therefore your model wouldn't learn anything. If you take a big model, and if a large number of your nodes have values that are extremely close to each other, that is difficult to distinguish from each other, effectively it's symmetry, and your model loses the ability to learn. And you can also have the opposite. Weights could be so far apart in their spread that you have wild swings. So what we need to do is to have, when we start training, what we call numerical stability. So I'm going to show you an example of a model where we don't have numerical stability, and we build this absent of any methods to protect us from it. So we're going to take the minced example again, and this time I'm going to build a deep neural network with 40 layers. Each one of them have 64 nodes. Now that's really deep. This thing should be really accurate. I should get 99.999% accuracy, but we won't. So let's go ahead and train it on that and look what happens. So we start off here. We'll just look at the accuracy. So we start at 43, 72, 75, 74, 78. And then about here, suddenly it changes. It drops down to 70. Then it drops down to 68. Then it starts to rise again. So what we're seeing here is numerical instability in our model. And it's likely going to swing back and forth like this. Okay. So this kind of leads us to also to the concept of overtraining the model. Okay, so in convergence, which we talked about in both part 1 and part 2, it's really when you're training the model, you're minimizing that loss, and at first it's sort of steep drops in the reduction of the loss, and then it slows down, and it finally plateaus out. And at the plateau, we call that convergence. But if we train past that, we have a problem. If you recall, we design models to have overcapacity, redundancy to them. And in that redundancy, if we overtrain, it can start memorizing the examples. It will appear in the training data, or accuracy will go up even more, but when we run it on the test data, we'll see the accuracy will degrade. Other problems that contribute to this is the fact that our layers don't learn in a uniform manner. They have different convergence rates. So some layers may be working to convergence while others have already converged and will start diverging. So we kind of need to find that sweet spot. Oh, and another problem is, even if we're converging, even if we're doing a good job, if we overtrain, we may actually pop out of that good local optima we have converged on and start converging on a different local optima that's going to end up being less accurate. So here I'm going to show an example of overtraining on a simple covenant. This one, we're doing it with the CFAR10 data. And if we look at the first few epochs, we have 52%, 66, 72, 77, 83, 87. So on the training data, we're progressively going up. It looks good. But let's look at the validation accuracy. So we start off at 63, then 67. So it's in the same range, right? 68, well, suddenly we're 4 percentage points apart. Looks kind of suspicious. On the next one, 69 to 77, we're 8 percentage points. We're even getting further apart. The next one, we didn't really improve. 68, 83, we're 15 apart. By the last one here, just on the 6th epoch alone, we are 20 percentage points apart. We're clearly overtraining. If we keep training, we might, and we didn't look at the validation data, we could be fooled. So here, I'm just showing you what it looks like at the later part. So on the 11th epoch, I'm already at 96% accuracy on the training data. On the 20th, the last epoch, I have 98.5%. This thing is doing great. But on the validation accuracy, you can see it never really changed. It just stuck around 66%. So one way we can do this, well, let me say first is, one thing you could do is you could, set your validation split and visually watch the training. And when you see that separation, interrupt the training. Well, that's not really ideal. One is you have to be there and you have to be watching it. And you have to be cognitive that that event happened. If you catch it too late, you sort of stopped, went too far. Okay. So in Keras, we have this concept of checkpointing, and it's a way to tell when you're training to stop early. Oh, excuse me, that's early stop, to record what the accuracy is. Okay. And the ability with checkpointing is that after every epoch, we're going to record basically the model parameters and the current hyperparameter settings. So if we overtrain, we can actually go back to an earlier checkpoint and resume the training of our model without restarting from the beginning. Okay. And we could look at the checkpoints and see that there's one that meets our goal already. We don't need to resume training, and we just pick that checkpoint as the model that gives the best results. So let's set a checkpoint. So each checkpointing occurs at the end of an epoch, and checkpoints are implemented as a callback to the fit method. So we have another keyword argument here to fit called callbacks, and you give it a list of callback functions. So in this case, we're going to import from Keras callbacks the model checkpoint method. And what it does is it's going to take a file, and at every checkpoint, after the end of every epoch, it's going to record that state, the model state, its parameters and current hyperparameters to this file. Now, we kind of want to make this file name not a static name because we'd just be overwriting it, and that really wouldn't help us. So we're going to actually give it a file path here where the file name will get updated by each epoch number. I won't go into the string format syntax because it's a Python thing. If you're not familiar, you should just refer to a Python reference. But what's going to happen here is this going to be on the first checkpoint. This is going to be a 1. On the second one, there's going to be a 2, a 3, and a 4, and so forth. So let's assume when we were training that the best checkpoint in the output that we saw was checkpoint 3 or epoch 3. So that's the best checkpoint. We can go ahead and restore the model from that saved checkpoint using the load model method from Tensorflow+Keras models. So we're going to do a load model on that checkpoint, and that will restore the model with the weight at that time, in this case at the end of epoch 3. Now, we can also do checkpointing different ways. In the mints and the CFAR, it's not that expensive. But when you're saving the weight, because they're float 32, you're saving 4 bytes per weight. Now, if you have a few thousand weights, that's not so bad. But let's say you have 100 million parameters, okay? Well, on every checkpoint, you'd be saving 400 million bytes or 400 megabytes. And let's say this is a huge model, lots of training. It takes 1,000 epochs. Well, save 1,000 of those, and you've just written 400 gigabytes of data to your hard drive. It's probably not a good idea. So in those examples where you have a large model and a large number of epochs, you want to control when you write a checkpoint. An easy way to do it is with the keyword parameter period. And that just says every nth epoch, I'm going to write out a checkpoint. In this case, I said 4, so it'll be every 4th one. Another way to do it is to use the keyword parameter save best only. And this says I will only save if it's better than the last time. And now you got to give it a measurement for how to do that. Okay. And typically you could say things like validation accuracy or loss. In this case, my example, I'm using the validation accuracy. And so if, say, is the first checkpoint, right? Let's say at epoch 1. Then at epoch 2, it's going to ask, did my accuracy go up? If so, it'll save that one. If not, it won't. And so forth and so forth to the end of the training. So at the end of the training, the checkpoint that is saved was the one that was best, in this case, validation accuracy, throughout the whole training. Now, so that's great, okay. But even let's kind of think about it. If I have a few hundred, or no, in this example, let's say I have 20 epochs, and they take 30 minutes to train each. That's 10 hours of training. But let's say my objective is met after the 8th epoch. And it would be ideal if I could terminate the training then, saving 6 hours of resources. That's what early stop does. So this is another callback that you can add to the fit method that says, when you meet your objective, I will go ahead and terminate training early. And you can set things on basically like the level of accuracy or convergence on the evaluation loss. So let's go ahead and set up an early stop checkpoint. So from Tensorflow+Keras callbacks, we're going to import the early stop method. We're going to instantiate it. In this case, I need to specify what I'm going to base it on. That's the monitor parameter. And we're going to do it based on the validation loss. And so I'm just going to add that as a callback during training. So in this case, as long as the validation loss is going down, 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 getting smaller, we're minimizing, it'll keep training. But if at the end of some epoch it didn't, it went the other direction, it went up, it would automatically stop the training. Now, sometimes when we're training, there is a little variance. Sometimes that validation loss is going down, 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 and then it gets stuck for a moment, and then it goes down, down, down. And we wouldn't want to, in that case, prematurely stop the training. So there are some additional keyword parameters to early stop to sort of set that variance. So one of them is patience. And so in this case, I'm just saying, wait 3 epochs of it not going down before I stop early. Okay, so the next thing to talk about when we've referred to this to some degree in part 1 and part 2 are parameters and hyperparameters. Now, parameters are the weights and biases that are learned during training, and they stay with the model after it's trained. Hyperparameters are those parameters like epochs, learning rate. We use them to train the model, but they're not part of the model after it's trained. So what do we do with hyperparameters? Well, they're used to improve the training of the model. For things such as how long does it take to train the model? How fast does the model converge? Does it find the global or at least a good optima? How accurate is the model? How overfitted is the model? So the most basic hyperparameter is the number of epochs. It's not so important anymore. It was before. For example, we had checkpointing and early stop. You had to sort of predict the number of epochs you needed. If it was too few, the model wouldn't get fully trained and you'd have to start over with a higher number of epochs. If it was too long, you probably overtrained. Okay. Now, in place of epochs, we have another idea called steps. And in steps, we're referring to a sub-portion of the training data on the entire during an epoch. And this kind of comes from a statistical background. So let's go back to our idea of a population distribution, such as I gave of shoe sizes of all males in North America. If we had every single example, we'd have a population distribution. And we would know the actual mean, standard deviation, and the size of that population. And in statistics, we call that the parameters. But let's say we don't. But if we were to take any random sample that had, say, a bunch of different examples in it. So let's say one random sample, we went to 10 different shoe stores in 10 different states and asked 5 people what their shoe size was. So we had these 50 examples sort of randomly collected. That would be a random sample. And so it would have a probability of how much that random sample is representative of the population. And so that's where you get the idea of statistics. You have a mean, a standard deviation, a size for that sample, random sample, and you would hope that they were the same or equal. Well, the reality is in every random sample, they're not. Some are a little less, some are a little more. But if you collected lots and lots or more of them up, they would start to converge and they actually would eventually be representative of the population. So this is kind of what this diagram means. So if I collect up enough random samples, even though it's only a fraction of the whole population, their average mean would equal the and distribution, standard deviation, would eventually approach that of the population. And so what STEPS does is I'm going to say, as I'm training, instead of taking all the training data, I'm going to take a subset. And I'm going to treat my training data as if it was a population, and that subset as a sampling distribution. And what I want to do is each time it's a different subset. Now, if you remember me earlier saying when we talked about an epoch and the entire training data, even though we sort of reshuffle and make the batches different each time, it always sees the same sampling distribution. In this case, we see different sampling distributions. And one of the benefits of it is, one, we don't have to run as much training data during training. We can train faster. And we get this effect of different sampling distributions that if we average them out, they will start approaching the mean and standard deviation of the population. So the fit method has another keyword parameter called steps per epoch. And this is just a subset of batches. Okay, so let's say your training data based on your batch size would have 5,000 batches. If we said steps per epoch, we would only take 1,000 batches through during an epoch. But on each epoch, it'd be a totally different set of 1,000 batches. And therefore, each time it's a different instance of a sampling distribution of the population distribution. So the next hyperparameter is the batch size. And there's variations of it. It depends on how it's going to affect the gradient descent algorithm. So these are sort of the historic names. So the first one is called stochastic gradient descent. And this is where the batch size is 1. That is, we're going to update the model after each batch through and we're training. In batch gradient descent, it's the opposite end. We're going to run all the data through the model. And then after to do that, we're going to calculate the loss and use that to update the model at the end of each epoch. Now, the problem with the first one is that I could have big different changes in the weights. I mean, in the examples. So one example, let's say, could say go left, and another one is so different that you go far right. Okay, and if I have those big difference in examples next to each other, then I'm going to have these big swings of updates in the model. Suddenly, all the weights are all going to the left, right? Something on the next example, oh, they'll now shift to the right, and then back to the left, and then back to the right, and the model is chaos. It's just not going to learn. Typically, that method doesn't work. Plus, there's a lot of overhead. I'm updating the model after every example. But there are benefits to it because it's seeing every example as it is. Okay. Now, on the other one, because I do the whole batch, I've actually smoothed out the differences. Even though inside the training data there are big differences, by averaging it out across the entire training data, I've smoothed out those differences. So I'm not going to get the wild swings. But the problem is, unlike stochastic gradient descent, my updates are going to be really tiny. And I have to run more epochs. And so it's going to be very expensive to train. So mini batch means trying to find that sweet spot between the two, between running one at a time or all of them at a time, some subset. And that's what we call our batch. So typically when we set batch sizes, people start usually somewhere between 32 and 128. And they're typically multiples of 32. And this has to do with the hardware and efficiency of it. Or I mean multiples of 8. But on extremely large data sets that we're going to run on very high-end hardware accelerators, it's common to see much larger batch sizes of 256 and 512. And so you specify your batch size here as a keyword argument. If you didn't, it would have defaulted to 1. Now, the learning rate is the most influential of the hyperparameters. It has the most significant impact on the length of time to train the neural network, whether it converges on a local, lesser optimal, or the best global or best optima. And the learning rate gives us the means to control the degree that the model parameters are updated. Basically, it acts as a fixed coefficient between 0 and 1, and it's multiplied against the value to add or subtract against the weight. So we're kind of compressing that update down. And the more we compress it down, the more stability that the model has as it's updating, the less likely it will wildly swing back and forth. But we have a handful of problems if we get too small, just like we get too big. So let's kind of look at the difference here is, let's start with a small learning rate. So 0.001 is like a really small learning rate, and it definitely will eliminate large swings in the model parameters during updates. And this generally will guarantee that the training will converge on some local optima. But the negative side is we're going to take more passes over the training data because the rate we're updating the weights is so small that the loss we're reducing is reducing in smaller increments. That curve's going to not come like this, it's going to be more like this, much longer to train on. The second thing is that we're unlikely to explore other local optimas. That is, whatever optima we're on will appear to the model to be the best because it's making gains on it, and it will keep diving and converging on that without exploring other ones. And so in case it's a poor local optima, we won't get a good result. We'll overlook a better one. And there's also the problem of saddle points. And so you can't think of a loss as sort of a straight line or a curve. Sometimes there's like a plateau, okay? And if I'm on that plateau and I'm going to change my weight, so I go a little bit to the left, a little bit to the right, obviously I want to either, find that part where it starts diving down again. But if my updates are tiny, I may never reach that edge of that plateau, and I may just sort of go back and forth around this point on the saddle point and never get off of it. So now we could use large learning rates, do the opposite. Let's say 0.1, where we're going to cause big jumps in the model parameters during updates. And at first, at least in some cases, it will initially lead to faster convergence. We're diving very fast, less epochs. But even after you do that initial fast convergence, those jumps may start to overshoot and start causing the conversion to swing back and forth. So as we get deeper into the optima we're diving into, we want smaller and smaller updates. If they're large, we may bounce back and forth in it, or altogether hop out and start diving down a different optima that is less desirable. So in practice, there is no perfect learning rate for all data sets. Every data set has a different ideal learning rate, and it's also dependent on other parameters such as your batch size. But typically, they're going to be between this range of 0.1 and 10 to the minus 5. Now, another thing, as I mentioned too, is we don't really want to train with a fixed learning rate, let's say like 0.01. That as we're converging, we want to slow down those updates even more so we don't bounce back and forth or jump out. And we do that with decay. And this just means that we're going to reduce the learning rate by some small amount after every epoch. So it gradually decays. Okay, well, that's part 3. Thank you for watching. We do have a follow-up lab exercise. If you go to this bit.ly short link, it will take you to our GitHub account. And for those, of course, who have done this before, we encourage you to go ahead and relaunch it in Colab. And thank you.